purposes of this, and we'll figure things out along the way. So this is mostly to show, like in real time, how a computer could be helpful whenever you're like stuck with a problem. And I'll use as examples the homework that Benoit sent. So I'll try to work out some things related to the questions presented there. I'll try to do this on the fly, so the odds that there are mistakes are high. Feel free to correct me or to suggest even the next steps, like what to do next. So I'm also trying to encourage like participation and sort of trying to do more research and less presentation, and so a more active role and a less passive one. Okay, so that's the plan for today. I'll be mostly working on questions 1, 5, and 6. And we can even, move forward in the sense that if somebody has an idea about what to try or how to do things or what should be the next step, absolutely feel free to let me know. Okay, but I'm trying to sort of convey the idea that computers are powerful and they are helpful. They may, they can prove things, but I won't enter that today. Or I'm not planning to do that, maybe some other day. But they can definitely help a lot, providing what is the right theorem to prove, okay? Gaining a lot of intuition and figuring out, what should I prove if I want to do certain things? What's the right answer? So, yeah. Also, having said that, I'm going to use mostly Mathematica. Keep in mind, none of this is going to be rigorous. I won't prove any theorem. Mathematica may make mistakes. It's a black box, so you should double check sometimes. And if something is odd and it just doesn't match, it's unlikely, but sometimes Mathematica makes mistakes. Okay, so also keep that in mind. Like, just don't trust blindly what the output is. But okay, in 95% of the cases, the output is going to be correct, and at least one is going to get a good intuition and a good idea of at least what the answer is. Okay. So yeah, I'm going to start with 1, which was the following ODE. So is the font big enough? People can see this? Okay.
How can you share this? Can you?
I'm not sharing?
On Zoom?
Oh. Okay. Yeah, so pretty much, the code is self-explanatory, but it's something, and of course, have to learn the syntax every time, but it's clear what you can do, right? So I'm calling the following ODE, f double prime equals 1 over f squared, and the goal was to understand the dynamics as r goes to infinity. Okay, so we do that. Well, Mathematica is unfriendly today, and it says, well, I'm not going to solve it, but it's the solution of this implicit form.
So wait, is it 1 over r squared times f over r?
We can do that.
The linear of the
Oops. Okay. Then this is a lot easier. Yeah, so here there is not a lot to say, in the sense that this is the solution, and depending on the initial conditions, you get one row or the other.
just so this is the the Schrödinger operator that you saw. So before it was the Hamiltonian,
Right.
and now it is. So I'm confused. Problem one wasn't it the Newtonian dynamics in the one of our field radially? Isn't that R double prime? Is
I think it's an
negative P
example.
prime and R? I'm confused.
Okay. Yeah. No, I mean,
Sorry, Javi, you were right. You were right. Yes, you were right. I just got thrown off by R because for you R is time.
yeah. Okay. Sorry. My bad. Oops.
And where you're, can you call F R?
Sure.
F the R.
Yeah, absolutely. Okay.
So, yeah, maybe this is more interesting. Because here we sort of have an implicit relation, so it's not really solving. So let's try to see if we can do like a WKB. And try to see if we can extract the the leading powers as R goes to infinity, as T goes to infinity. So let's forget about the squares, pretend that everything has a good sign, and then we'll figure out and we'll talk about the constants later. So if I take square roots here, P is large enough, then I should try to write down R of P as a function of P. Okay, so ideally what they would start doing is to say, well, let's try to expand this as a series in R of P.
Sorry, I need to mute you.
Sorry.
Can you do it?
Okay. So now there is some echo. I should mute myself. Okay. So if I were to do a series of this as a function of R of T at infinity, and let's say to order 2, okay, there are some issues here because Mathematica doesn't understand very well what is C1. So this, and of course, since C1 could be real or imaginary, then there are like these floors and then the argument of a complex number and so on. But if let's say we forget about this constant is going to be 0. And we look at what we have. So this has to be equal to T, right? So what's the leading order? So the leading order is R, and then there is a log R. Okay, so our model problem is something like T is equal to R of T plus log, okay, maybe some constant, log of R of T.
And
Can we tell Mathematica that C1 is positive?
Yeah, absolutely.
What happens if we do that?
or at least that you're looking for real functions.
That's trickier. We could tell that C1 is real and positive.
If that's what we want.
Yeah, I mean, if we look carefully at the argument, this is going to be either purely real or purely imaginary.
Yeah.
So then this whole floor is going to vanish.
Yeah.
So this is gone. This is just an artifact of like Mathematica trying to be smart and generalizing everything.
Sorry, you can also make an assumption on R, like telling.
Yeah, I could do.
What's under the root is
Exactly.
I could simplify it like this.
What is on the square root? Maybe that's like the condition that you want to put as well.
Okay,
So C1 bigger than 2 over R of T.
let's help it even more. Yeah. Okay. Wonderful. Thank you.
Yeah, sometimes there is some back and forth interaction. Yeah, so the model problem is R of P, let's go of R of P plus lower of the term is to be equal to T. Okay, so essentially, this is suggesting that R of T is T minus some constant or T plus some constant log of T.
right? I want to, okay, so this is plus dot dot dot. So I want to invert this, and then I can take r of t to be equal to t plus some constant log of r of t plus r2 of t, right? That would be kind of the idea. So if we do that, then well, I mean, we can even substitute just without the log. So the leading order is t, right? So then r of t. Okay, so now if I were to do this, then the r, so plus r2 of t, this is what I want. And then I substitute this by t plus r2 of t, right? This would be, and this is an r2. This would be the hope, so that then I can solve for the next term. And yeah, oh, well, okay, this worked. I wasn't expecting it to work, honestly. Yeah, sometimes, yeah, I did this kind of on purpose, because sometimes it just tells you that the solution is the solution of the ODE you just wrote. And, you know, of course that's true, but it doesn't give you any additional information. And it is a bit slow sometimes. Yeah, okay, great. So you full simplify and then no solution. Fantastic. Okay, so let's try to outsmart it. And then let's say, well, we are expecting R2 to be low order. So then let's keep the high order on the right hand side and see if by doing this we can get better and better expansions. So
Or can you assume that yes, no, R2 may not be positive, or at least you don't want to assume?
I'm not assuming anything about R2 at this stage. Just that it is low order with respect to T. So, okay, so like that didn't work. I mean, of course, this one is going to work.
We are just doing random examples, right? Or these are connected and I cannot connect.
Connected to what?
Like the original problem that in Benoit actually.
Well, they're connected to problem 1
Okay.
of the.
Maybe at least it's good if you just write and recall the ODE.
Can we immediately reduce the cost order using energy consumption?
Okay. We could do that. I was just being like dumb and then turning the crank.
If we write the thing on the board, then we can do, or ask Mathematica to get energy consumption.
So I did that exactly. So Mathematica actually gives you like not an explicit solution, but in terms of like the inverse function with respect to something. So if you try with the cursor on the Mathematica is gonna,
Do you have your laptop?
yeah, actually.
Maybe it's easier to just plug
I
it
can
in.
just pass you the code.
Or just plug it in.
Yeah, but the exact solution of this problem is given by the parameter equation. So I guess the Mathematica has some point there.
Maybe here we can get away with it, but if we had like something more difficult, yeah, no.
So
I'm just sort of doing the WKB by hand. Literally,
I can
this
tell you
is
the equation that
this
I
is what I'm doing.
did.
Just come here, take the laptop and plug it in. It's easier.
Yeah. I mean, it was nothing super smart, just trying to get it Mathematica gives me the answer.
Right.
So there are two of these, right?
Or you want to show the code?
Yeah, I'm gonna write the equations just in case, so.
¿Qué tienes?
What should I say?
Prueba.
¿Cómo lo llamabas?
RDT.
La que resuelvo yo.
Predictor.
Cuadrado. Con la
1 menos 2 partido por eso.
This is the one that I obtained using energy estimates, and I think this should be the equation. I normalize the energy to be 1 or 2. So this is what Javi presented. I don't know if we are seeing something.
No, but you can, it writes it out as an inverse function of something.
Yes, which I plotted to understand what was going on.
Cannot see this.
Yeah,
Vale.
no estamos con el tuyo, es que no sé cómo.
Ah, vale. Okay. Yeah, we'll do it on my.
Yes, lo siento.
No, no pasa nada. Okay, so then we have.
Cuadrado. 1
menos 2. Right, so then, okay, in this case, we could just simply look at this and extract the asymptotics out of here. Right, this is easy or easier. Yeah, like the sharp one in this context means that this is the variable. So it's the inverse function of -2 plus y divided by the square root of -2 plus y divided by y, da, 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 da. Okay, so that's, yeah, that's what Mathematica speaks. In principle, we could then do like for mathematics here.
It gives you two answers that correspond to plus or minus because you've only given r prime squared and not.
Yeah, so it's the inverse function of this whole thing evaluated at -c plus c or c plus.
And what's the and? There is some and symbol.
Sharp.
No,
at
the end of the
I think this
parentheses
is the
The
start.
notation of the function in Mathematica.
Yeah, exactly.
of inverse function.
No, I think this is the thing that this whole thing is an average.
You have to put the argument.
So this is what you feed to inverse function, and this is the variable.
Okay.
It's just notation. Okay, so this is a clever trick. Let's suppose, yeah, sometimes you need to play around because there is some magic inside and you need to shake it a little bit and the Mathematica. So sometimes even like equal formulations feel like sometimes it can do it, sometimes it can't. Especially when it comes to integrals. So yeah, you have to sometimes play with it a little bit. Suppose that we didn't have like this, and we were just to start doing the the WKB by hand. So if we were to do that, and we were here, so R was T plus something, then okay, this is already encompassed by the T. This is a translation that we can take it to be 0 because then we translate everything by C1. So we see that the next term should be 1 over log T. Right. So then we come back and
wait, how did you see it? Sorry, can you see it?
Because this is what Mathematica is outputting for R2. Of course, there are always higher order
because
terms.
now it's just 1 over t squared.
Right, exactly.
Okay.
So now what we do is we simply expand. So we call R2 plus plus or minus log T.
So coming back to the inverse function, can we ask Mathematica to do a series expansion?
Absolutely, yes. Absolutely. Let me take C1 to be 0. Okay, yeah, sometimes this happens.
What does the 2 mean?
At the order of the expansion. Right, so
And Mathematica already understands that it's dominant term and then the first subdominant term? Or like
no, not necessarily. It would expand up to order 2 or order -2. I mean, so it would expand.
Don't you expand according to a scale? So in polynomials or in terms of log, or if
That's
you don't
right.
tell it?
That's right. And then it has some criteria about when to stop. It may mean 2 terms. It may mean up to whenever the power is 2.
It's exponential growth at infinity. Does it give exactly e to the?
Sometimes. If it is easy to find, sometimes it does. It may get confused, especially if you have like exponential of log of something, then it may get sometimes confused. So yeah, I think it's easier instead of expanding the inverse function, expand the function itself and then solve implicitly for the equation. Yes.
So the argument #1.
Yes.
Is it negative, positive? Because if I look at the denominator, I see minus #1 squared. So then I have something imaginary in the denominator.
That's right.
Um,
You may, it depends on the one, yes.
if it's a real argument, then I have everything's imaginary in there.
No, but I think one,
Yeah.
because of the constraint that Bruno said, this is smaller than 1.
Yeah, also you can see it on before when you have the 2 minus.
Or smaller than 2, sorry.
I see, so it's a small quantity. Okay, okay.
And just in the way it's written, so the sharp one, you have sharp 1 and t, like somehow you do the inverse function and there is no t
No,
in the expression.
yeah, because this is a function of t. I'm inverting this onto t. This is what this means. So I'm solving t is equal to that thing. I mean, I'm trying to invert that.
But I think the easiest here to help it out is to just compute the expansion here and then invert by hand.
What is and signal mean?
What is what?
What is and signal?
And
You mean the ampersand?
Yeah.
yeah, this is the argument of the inverse function. So this is just saying that what it comes before it, it's the argument that you feed.
Javi,
Yes.
we noticed that there's something weird. I mean,
Yes.
for some reason, the first factor with the radical has a y-2.
Yes.
And then you see, yeah, I don't know. You see what I'm saying?
Yeah, I see what you're saying.
I don't know, it's weird.
But this is probably going to be cancelled by the denominator, no?
Yeah, so you have y-2 in factor and you divide by y-2, no?
Exactly.
So maybe we can simplify by hand. That's what that's weird.
Yeah.
Right,
Because both sides have the same.
the other thing, dark sign and the
Yeah,
other.
I also noticed there are a lot of calculations that you're gonna do by hand.
Yeah, so
Sorry. Yeah, so Mathematica has these
Just
things.
put it in the formula, I guess.
Yeah.
Yeah, maybe let's. So the first thing I would do is like just to plot this as a function of y
Okay.
and see how it looks like. So this is bigger than.
Yeah, now
I think it seems to be purely imaginary. But actually,
I mean, it's probably
some
way
hyperbolic
bigger than
side.
one.
Some parabolic side. Yeah.
maybe it's why bigger than 2.
Yeah, I mean, I don't know. But we are
Yeah,
so
that
we are
would make
inverting
sense.
this, so we should really look at whenever this function goes to infinity.
Right. So then we should be looking at the case where y is bigger than 2. And then probably now the root is there is an I here and there are eyes everywhere, and this is where still like the I outside.
Yeah, I think you divide by the y minus 2 outside, so the only thing that survives is root of -1 at the denominator,
That's right.
and probably the arc sign of something imaginary
Arc
is also going to cancel that.
So here is something that drives me crazy when I work with Mathematica and Maple. Why is it so stupid that it doesn't cancel?
Because it is trying to make it in so like full generality that it doesn't understand it.
So what if we do a full simplify just on the inside of real imaginary? Will it get rid of this or cannot get rid of it because they're different branches? I see. It cannot.
Exactly.
Unless we tell it.
That y is bigger than 2. Yes. Yes.
Let's do a full simplify with assuming y bigger than.
That's right. That's right. Yeah, that's the problem. That sometimes it tries to make it in so much generality that then it leads to these confusing things. So yeah, so we could expand.
That's
And then it does give the, well, I mean, to. So you see, this is the thing we were discussing. So
sounds
it
very
does
nice.
expand up to order 2 because I told you to expand up to order 2. And then, but sometimes if you have products and things, then it may do weird things. So try to be a little conservative when it comes to the order, like maybe put 1 or 2 more than what you actually need. Yeah, so then we would be solving essentially T is equal to all of this, and that would give them the asymptotic expansion. I mean, no, that thing evaluated at T is equal to
R.
To R. Okay. So we could just simply yeah, just start solving and do the WKB from here, or as before, start doing the WKB from the ODE and turn the crank. I mean, all of this I'm doing it in a very simple way. Of course, if you want to compute an expansion to order 1000, you can always program it and do it in a, let's say, in a more systematic way.
And just a terminology. So to me, WKB would have been a method to solve Schrödinger.
It's not constrained to.
So you just said
ODE
this
or a
is,
PDE.
you put the first term.
So can we try the WKB with Mathematica?
Let's do 6. For
I
that.
see.
Yeah, so 6. Because 6 is exactly this. So we have LF sigma squared.
And LF was D RRS minus 2 for DRF.
We have a potential here. Plus 1 over. Right. And okay. Let's pretend that sigma is real. I mean, I could write real part of sigma, but for now, let's pretend it's like this. Okay, great. So yeah, our favorite different special function. So good. So now we have all the thing, and probably the definition of these functions are the functions that solve such an ODE. But let's try to do the WKB at absolutely.
For sigma 1, I have 1 over 10.
Yeah, in fact, yeah, I'm probably going too fast. That's what I would do if I didn't know what the out like what the result is.
It would be extremely nice to see something.
Oh yeah,
And what's the difference between the U and F1?
right.
I think I also want to see when we take sigma as I. Can we also, is it possible to do something else?
Absolutely,
I
yes.
mean sigma squared as I.
Yeah. Okay, so
April, what was your question?
When sigma squared I. So I was
I,
just
yeah.
trying to understand what to add exactly into the extension.
Sigma square.
sigma squared is equal to I.
So that's actually, yeah, like which cutoff it's gonna take, that's also.
But your assumption is sigma is positive, so.
So in here, you probably it doesn't.
Yeah, let's take sigma to be 1 first, and then later we'll do the other one.
Can you explain the syntax? What is
Sure.
slash dot?
A slash dot means substitute in the previous expression all occurrences for whatever I put, and by whatever, like on the left, by whatever I put on the arrow. And I can do here multiple substitution. I mean, if I were to substitute also R, then I would do something like this. I mean, of course, now this doesn't make any sense, but yeah, so the slash dot means replace by, literally replace by. Like don't simplify, don't do anything. Whenever you parse the previous expression, replace left by right. Nothing more intelligent than that. Then later you can do a full simplify, but the slash dot only replaces in the parsing of the previous sentence, let's say. Okay, so suppose that we were to do this from.
Just to repeat this, so it doesn't create a function and then evaluate it at sigma equal 1. It just replaces the string sigma by the string 1.
That's right. And then, I mean, of course, it evaluates it when it comes to the plot. But
by that time, it's.
But by that time, it is parsing a 1.
Yeah.
So you can think of this as being like some preprocessing that is telling Mathematica, like, okay, take this sentence and replace. It's like a find and replace. It's literally that. And then when it tries to do the plot, then it does the parsing and finds out that there is a 1 there. There is no memory of a sigma being there anymore. Right, so we can take the real part, for example, and the imaginary part. Okay, so if we were trying to understand the asymptotics close to 0.
So this is purely real, no?
This is purely real, yes.
So we get the 0 inversion.
Exactly. So usually Mathematica has the following code of colors. The first function that you plot will always be plotted, if let's say by default, will always be blue. The second one will always be yellow. And then I think it's red and green.
And can we make the right cutoff bigger so we see oscillations like 20?
That's right. So we could do, for example, 100 to 1,000. Now we see lots of oscillations, and you may okay. So watch out, because sometimes we see this, and maybe this is not. In this case, it's an oscillation, but sometimes Mathematica may have like precision issue, so that then this is garbage, because it's just oscillating and it's like telling you nonsense. So we can think, well, I mean, one simple way to figure this out is to zoom in, but let's say we don't want to zoom in, and we just work with more precision. Mathematica can do calculations with arbitrary precision. You need to be careful with the syntax, because if you write one, you need to tell it that that one has 100 digits, and we don't write it as one. You need to write it as one with 100 digits, and so on. But you can do that. So okay, I increase the precision. Then
what's 100 there? What's the number 100
digits of precision.
digit of precision?
Yes.
Does that even make sense?
Yeah. In what sense?
Most computers don't work in more than 32.
No, that's not right. No, you can work with arbitrary precision. You just define your floating point numbers and the floating point arithmetic to use like more chunks of 32, 64, and whatnot.
Can go with that arbitrary, like 100.
No. I mean, I've done calculations with thousands and even millions of digits.
Mathematica knows how to work around that.
The thing is, if I put there a million, I may not be to see it. Okay? But that's a different story. But if you do these things in a faster language, you can certainly work with hundreds of thousands, millions of digits, no problem.
And what was your thing with saying that one has 100 digits? So when you, for example, when you substitute sigma goes to 1?
Yeah, no, here these numbers now are not in 100-digit precision because the way they were entered. So you have to be a little bit careful if you're trying to compute everything with like lots of precision.
But then how did it even understand if one of them is not?
Yeah, so this is what I'm saying, that depending on how you write it and depending on the internal ways of how Mathematica works, it may truncate some calculations at some point. But it may be useful to clean around, for example. Yes.
Can we do Windows 0 to 10 because the wavelength should be 1? It's
Yes.
one of the sigma.
Right, exactly. So this is kind of the more complicated way. But if we were to do, let's say, 10 to 20, then we start seeing oscillations.
If we do 0 to 20, then we see the non-oscillatory, but it's not very dramatic.
Right.
Or it shouldn't cut it off.
Okay, this is.
Yeah, nice. And so we see here that the solution became.
That's right.
Because we haven't multiplied by one over r.
That's correct. Yes. So let's now do the formal asymptotics. Oops. Okay, so we can still see some things. Yeah, it doesn't look like no, but yeah. So this line we can ignore it, and also this line. Okay, so what do we have here? We have some oscillatory term e to the I sigma r. This is also oscillatory because it's like r to the I, plus some coefficient divided by r. And we also have the counter term, e to the minus
sigma r, which is expected because the function was real in the first. So e to the minus sigma r, some number divided by n.
And this r to the I over sigma is extremely interesting because that's exponential of log r, which is what you had before.
Exactly. So yeah, that was literally the comment I was about to say. E r to the I to sigma is exponential to the log of r I over sigma. And this is also going to come in the oscillation. So then we're going to have roughly e to the I sigma r plus 1/2 sigma log r, some constant divided by r. These are the asymptotics at infinity. But we could do more and more and more. Like if I put here.
By the way, not to interrupt.
No.
But this is also extremely interesting. The I to the minus I over 2 over sigma. We saw that in the distorted Fourier transform because that's e to the minus, what is it, pi over 4 sigma. Right? Because I to the minus I is e to the log I, which is in principal branch I pi over 2. Right? And then we have I times I, so we get e to the pi over 4 sigma.
Right.
And Ibn will explain how this exponential to the 1 over sigma, at least very heuristically in a coarse grain, is e to the action computed between 0 and the turning point.
Right.
Yeah, no, absolutely. So this is the power series of the 1 of 1. And we could do the same for the other one, which is the U. Yeah. And the U is complex.
What does the plot look like? Okay.
Yeah, in the end, these are going to be the phi and the psi and the theta.
If you go upstairs and just copy your plot and replace everything by U.
Yeah, okay. Yeah, thanks. Okay, so something diverges.
Doesn't like it.
Well, it doesn't like it at 0.
Oh, because 0, yeah, it's singular.
That's right. So this is how it looks like.
Yeah, and the singularity should be log at 0. No?
Let's see.
What is this?
It's 1 over r.
Maybe log r.
There is a log as
log
well.
r over r, yeah.
There is a log as well, but the main term is 1 over r. This is fine because in the end we are taking r times
Yeah.
So it's gonna be a constant, yeah, that makes constant.
because of the weight in the
Yeah.
internet. There is an r square and then we split it.
No, because one of them should be singular even if you.
Yeah, you still
multiply
have the
by
log.
r.
And here,
I mean,
want
because-
to say something just
Sure.
right here. Like if you say the coefficient of 1 over r and log r, they're the same. And I have to check it out in order to write the self-adjoint extension of the operator that we were dealing with. I don't know, like that's actually required in order to find the self-adjoint extension that that the one that we need to work with. That is reduced from the R to the N to one dimension. I'll tell it later, but just here you see, so that later I don't have to explain in more detail.
Yeah, so this is in general, sorry, no? It's in general complex. So there are real and imaginary parts of this guy, whereas the other one was fully real. Okay, so that's also like a difference. I forgot what were the questions. So we figured out the asymptotics of, I forgot what.
But just so Mathematica gives you, if there are two solutions, a real one.
Yes.
And then is there any, how does it chooses the other one?
No, there are coefficients in front. There is the C1 and the C2.
Yeah, so it has to find the basis of the set of solutions.
Yes.
And one of the base, I guess it chooses the real one if it exists. And then the other one, is there?
If the other one, you can compute the constant, for example, and once you have one, you can figure out the other one.
Yeah, but how does it do it? It's
This nobody knows.
okay, so just chooses another one.
Yeah, that's Mathematica is not open, so you don't really know what is going on inside. But it does give things that look correct in detail. And we could figure out, like the envelope of the amplitude, the oscillations, like here again, this is the U, or this is the U. So here we don't see, oh wait, sorry, this is at 0. We could do this at infinity. Right, so now we see also oscillations, again, with this 1 over 2 pi log r. So we need to the minus sigma r, never mind this 1 over r, and we have like the extra log of I effects. And in the envelope, we have this 1 over r. Okay. So this is, and we could do in principle this up to any order that we want. So this is telling us already like what should be, I mean, of course, there's no proof whatsoever, but it's telling us what should be the right behavior at 0, the right behavior at infinity, and what should be the recipe for computing the basis of the distorted Fourier transform. Okay.
Can we see a few plots of the Whittaker M? Because that's the fundamental. So in other words, if we do conjugate your ODE there by R, so what you computed as function F, we multiply by R, we get the Schrödinger without first order term, right?
Right. But this would yield the same solution as if I multiply this by R and the other one by R.
So isn't it 1F1?
Mathematica will give us Whittaker M, Whittaker W, or hypergeometric.
It does give hypergeometric.
It does give hypergeometric.
But they are the same. I mean,
it recognizes Whittaker M as a function. No?
That's true, but when it comes to solving the ODE,
it spits out F1, 1F1.
Yeah.
Okay. Can we just plot, for the sake of sanity, a few of our disjointed Fourier transform, what we call phi?
Just before, can you take, so I just want to see the plot, if it's possible, when we take negative I sigma as 1 minus I over root 2. I mean,
sorry, that's start again. So
I want negative I sigma to be equal 1 plus I over the 2. Like root 2 is not that important. The root 2 all over. Yeah. I just want to see 1 plus I actually, like how it's done. That's good. Yeah.
Like, and you want me to have an I here in the sigma?
Yeah, this is exactly how I want, like negative I sigma to be done. Yeah, yeah, whatever. I mean, that was my calculation. I didn't calculate it this way, so.
Sure.
And just see the real part of it.
Okay. The real part of the U or the 1F1 or both?
Well, it will be better if I see both U and F. But
Okay.
They have
Okay. Yeah. No. that's-
But then isn't F just a real part of U?
Sorry, I can't think and type.
I don't think
Well, you have two solutions, and I guess both the real part and the imaginary part should be a fundamental system as well.
Okay.
I guess the difference of them because they have both singularities.
Really, I thought one of them did not, but
If there are no singularity, then that is because the other must have singularity.
in the plot of the, well, we'll see.
Okay, so this would be the U.
Zero, around zero, this is around zero, right?
This is around 0, yes.
Can we make it infinity?
Yeah.
No, I'm sorry.
No. Okay.
We won't see much because the wavelength is so small, it's only one, yeah.
Okay.
Yeah, okay, this is a problem. There are some numerical issues there. If you look at the scale.
The numerical issue is that
Yeah, it's the
Mathematica
scale. I
cannot
mean, it's 10 to the
process something that
38.
big. But I mean, if it's going to grow exponentially,
Yes.
Okay.
Because of the e to the minus I r sigma is imaginary part, then you have to check in its real part.
Right, exactly.
so
We could still do the asymptotics.
and maybe just like a ballpark, if you see that the scale is up to 10 to the 50, do you
That's
think
the
that
one
then it
that
doesn't do
will
it
correspond.
correctly?
If the sorry, can you say that again?
HF is
I
equal
could plot the
I.
log of it.
Yeah, but in the
So over
ballpark.
this
So
one,
probably at some
so
point, if the number is too big, then
minus
Mathematica,
Is it
you
exactly?
need to increase the working precision.
That's right, yeah.
So what would be the number that you say if on the plot you see a 10 to the 60?
No, that's too big. I wouldn't trust them.
Okay, so 10 to the 20?
Probably not.
10 to the 10 is kind of where my confidence starts
Okay.
to shake. But then if I see a
And
10
then
to
you
the 10,
increase-
then I react. I mean,
You
it's-
increase the precision.
Yeah, or I
understand
try
that.
to plot the log, or I try to manipulate the
To get some
expression.
idea of what you see it and you say, okay, this is
Right, or if
probably
I pre-multiply by if I guess, well, this is maybe growing exponentially, then I will put an exponentially more term in front.
Hmm.
I mean, there are all sorts of tricks that you can do, but they are driven by what you see. It's not a recipe where, you know, you do this, you do this, you do that. It's more
although
like
if you put the
you do
exponential,
something, you see something, and then you sort of act accordingly.
but yeah, I mean, like just putting an exponential term in front would not force Mathematica to multiply a very big number by a very small number. And
Yeah,
then,
but sometimes if you, for
Is it-
example,
it
if
is
you
smart
full
enough?
simplify first,
okay, it is smart
then
enough
maybe
to,
Mathematica can, that there are all sorts of like things going on that you don't have a lot of control. But where Mathematica may be clever and figure it out. Yeah, no, I agree. If you do the down multiplication, you end up with a big number times a small number, and then you're pretty much in the same spot as what you were before. But sometimes there are simplification rules, or like if you hit it with a full simplify, then sometimes it does actually simplify. So then you can try to take advantage of it. Yeah, so this is growing exponentially.
Enough for me. I like it, okay.
So that's, yeah, you have like here, the term coming from here, and here there is also like in the R to the I, there is also some growth. And we could do the same for the 1 of 1.
and why this particular value of sigma?
So remember in when you go to spherical coordinates, the one on the Hamiltonian on one dimension, it's not satellite joint. And I was looking at satellite joint extensions of that. And for that, you need to understand what is the kernel of h minus I and h plus I so that you can extend it. And then I had something like this, but I just wanted to make sure that what I had is right. So that, but I just used the book to see what is large expansion.
Yeah, I mean, this is easy and quick, so then it can give you at least an idea of whether what you're doing is correct and
What should you be expecting like out of it?
Okay. That's good. Thank you.
Yeah, and from here, okay, so I think this is 6. Yeah, I didn't try the longer transform, but
Never mind the language. But can you show us, here is phi r sigma.
which phi there are? No, phi, sorry, not psi.
Phi r sigma. Exactly,
Yep.
exactly as here, and then just, well, a few values of sigma, like 1/4, 1/2.
Mhm.
Is there a free factor on the phi?
2i sigma dividing.
Yeah, we will need that.
Yeah.
If it's imaginary. Yeah. Up to normalization.
Yeah.
That's right.
The other room was always warmer, but maybe not today because there will be more.
Yeah.
It's not an east room, so it's more than here. Yeah, so this is the auxiliary basement.
That's right. It's real.
We lost anyone.
Yeah, because.
Oh, okay. I think where did he go?
From a restaurant.
Oh, okay.
Yeah, this is what we expect. So what's the point of this exercise? So that it's more suggestive if we take sigma to be maybe 1/10. That's then let's see what happens. Then we have.
Yeah. Well,
Yeah, so then we see that the oscillations start much later. They start at 1/sigma, right? Yeah, and what April will explain, I think, is that WKB gives a very good approximation for the oscillations, but as far as April and I understand, WKB gives a very poor approximation, and we cannot use it to approximate the non-oscillatory region to the left of the tongue.
but can't you just approximate at 0 and do the WKB at 0?
Well, there you can use power series.
Oh, for example, yeah.
But so what is the asymptotics from 0 to the turning point? They are not so confident.
The error curve.
I haven't spent any time on it, but April and I did some quick calculations that show that if you try the standard WKB, because of the 1/r singularity of the potential, the standard WKB seems not to work. Correct, April?
You need the same for the both recursive and attractive case. I think for attractive case that's there's a problem for attractive, but I think for recursive because of the thing, so it may work. It may work.
Well, in WQB, so you make the ansatz the standard ansatz, then you get another potential, and that potential in the stretched coordinates, in the coordinates given by the action integral, it seems to have a 1 over W cubed singularity near zero,
But-
which is worse than what you started from.
You're just changing the sign, right?
Yeah.
Yeah, because I don't think you can generate a zero. You see the one side happens because sigma squared minus 1 over r will be 0. If you add plus 1 over r, then it's always gonna be positive, so you will not really have the 0 to
Yeah.
sigma part.
Yeah.
One over sigma. So Javi, kind of the hard problem is number 7. I have no idea how to do it. It's very relevant, I think, if we stick to this distorted Fourier transform approach at all. This afternoon we should debate that.
Okay.
But this integral probably Mathematica can do nothing with.
Right, and no, go ahead. But after that, can you just plug in either Whittaker M or W, but taking out the e to the I r sigma minus log 1 over 2 sigma log r?
Sure.
Sorry.
No,
And then we have P rho sigma of sigma d sigma. So what is that? That's the propagator.
Mhm.
So we have e to the ITL acting on a function f, and r is 0 to infinity. This kernel is
Mhm.
propagated kernel. And what are all these things? The phi is what you type in.
Yeah.
Phi or sigma is distorted. And it's one of many ways to write the distorted, but only up to a function depending only on sigma. Otherwise, it's unique. So April will also talk about that.
Yeah.
They write about the subplatonic extension.
Mhm.
This is unique up to a function that's only, let's call it kappa, only a function of sigma. And then you would have to compensate in the speckle method. So at the moment we have Whittaker M,
Mhm.
and I think if you look at Abramovitz theorem, they stick the parameters down here and the argument. The reason I wrote it in this form with 3 arguments is because Mathematica on April gives you the Whittaker M with 3 arguments.
That's fine.
So in Abramovitz theorem, this is called kappa, this is called mu.
Mhm.
And what is this? So forgive me, the spectral measure is sigma over sinh. By to sigma, it has these asymptotic near 0. It's like that. And Benoit, I know that you correctly suggested a different normalization that near infinity, we want the oscillations, they're gone now.
About
that we saw in Mathematica to have height 1, to look like cosine sine.
Right.
This normalization gives you a completely different dependency on sigma. And this was 2 pi over sigma squared and sigma tending to infinity. I was amazed by these factors, and I feel stupid to be amazed by them because you see them immediately if you just compute the action from 0 to the turning point. Does everybody know what the turning point is? This is what April will talk about at length. Here is the 1 over r. Here is the height of the energy, correct? This is sigma squared. And down here, this is where the energy crosses the potential. This is classically forbidden because you can't have potential energy bigger than the energy. And so here is where Mathematica showed us oscillations, and here where it showed us a completely different behavior. Where does this come from? Look at this integral, 0 to the turning point, root of 1 over r. No, I cannot call it r, or why not? Because this is fixed. What is this integral? Substitute r equals, what should I do? Sigma minus 2 times u. Then isn't this integral 0 to 1? Root 1 over u minus 1 du, sigma to the minus 1. that sigma to the -1 explains in some way that. Okay? Because in the Agmon metric that we will talk about, WKB, you deal with exponentials of the action. This is the action S evaluated, I suppose, at the turning point sigma -2. Everybody with me? So, Javi, this is a slightly terrifying object.
No,
What I challenge everybody to do, plug in 1, 1 and tell us what this does as a function of time, as time tends to infinity, but also towards 0. Okay, I tried a bit, didn't see much. What Mathematica probably cannot handle at all. How could it possibly deal with this? We would have to somehow change variables, but you have both sigma and you have 1 over sigma, so. And for us as a group, we might want to, so how do we even deal with Whittaker M? We would have to plug in an integral representation of some shape or form in a complex plane. There are these beautiful notes by Jiahua, forgive me if I don't pronounce it correctly. Right?
Yeah.
yeah, but the Whittaker
You
M,
explained Laplace's method very nicely, so that gives you immediately how to.
the Whittaker M shouldn't be a problem in the sense that we substitute by the appropriate
Well,
function.
whatever progress we can make on this is progress on the problem, but I think this afternoon we have to also be guided by the nonlinear problem and maybe treat the linear one as a black box and make a list of properties of linear flow that we want. So as to generate progress in the nonlinear problem. Okay.
But this is, I mean, okay, I'm very naive here, but this is all fixed. It's a fixed function. How hard can it be?
It's completely concrete.
Yeah.
So this would almost seem like a trivial problem and a waste of time to think about. Of course,
No. But I mean,
it should be easy.
Yeah, that's my point. I want to be encouraging in the sense that I mean,
It should
it's
be
one function,
correct.
no parameters.
What
no
could
nothing.
be difficult about this, especially if you plug in R and R prime equal 1.
Exactly.
And then it's a function of time. So please, anything you can think of. Method of steepest descent, but first you have to plug in a correct representation of the Whittaker M function.
Which is.
Yeah, but once you know, okay, so once you know the answer,
Proving it is much easier than if you don't know. And then you can do all sorts of tricks and control the errors and whatnot.
But so can we try it now? So
Yeah,
if you
okay.
plug in on Mathematica, we take care of, and we plug in
Yeah.
when R is 1 and R prime is 2.
sure.
And we plot it as a function of t.
Sorry, I can't see the board from here.
Maybe I'll stop the recording.